Hello and welcome to this lecture. In this lecture, we will look at some very common discrete distributions, as in some discrete random variables that will show up again and again in many applications, and they're very useful to get to know and be able to describe. And once again, like I mentioned before, we will soon start talking primarily about random variables, and everything else will be defined using random variables. Events will be defined using random variables, probabilities for events will be calculated using PMFs, etc., etc. So we'll get used to that idea slowly. So these common distributions will appear again and again and again, and you have to learn to identify situations where these distributions are reasonable to employ. Okay, so let's first get to know them, and then maybe eventually we will see some situations where these can be used and we'll get comfortable with them. Okay, so let's get started. Okay. So the first and most important random variable, in my opinion at least, is the uniform random variable. It's a very simple one, but still it's very useful. So my strategy for describing these would be to simply specify the random variable. How do I specify the random variable? I specify the range, I specify the PMF, that's it. And we'll keep proceeding. I'll give a few typical scenarios where, simple toy examples or maybe even more complicated examples where these occur. Okay. So the uniform random variable is basically, if you say, and this is a notation that we will use, so pay attention to the notation as well. So this notation that we have here, so this X is uniform T, okay, so where T is some finite set. Okay, whenever I put a finite set here and I say I have a random variable which is uniform in that finite set, what I mean is this random variable X has range equal to that finite set and its PMF is uniform, as in it takes the same value for every entry in that finite set, every element in that finite set. So it's 1 by size of T. Okay. So here are two examples. One is tossing a fair coin. Clearly X you can take as uniform 0, 1. Okay, and 0 I'm using to represent heads and 1 is for tails. And the next example is throwing a fair die where X would be uniform 1, 2, 3, 4, 5, 6. So now instead of 0, 1 or 1, 2, 3, 4, 5, 6, I could have any other set here. As long as I say uniform, it's clear what that random variable is. Okay, so this is a very simple and powerful, often used random variable. So often people make this assumption that random variables are uniform in a set. Okay, so how do you sort of think of scenarios? So if you are looking at a random variable and you think all its outcomes are equally likely, then that's where you start putting in the uniform assumption. Okay, so that's one way to think of it. So this is a simple random variable, and like I said, it shows up again and again. The next one, which is again very simple and again shows up all the time in applications, is this Bernoulli P, Bernoulli random variable. And once again, we'll use this notation. So you will see, you will get used to these what are called parameters of random variables. Okay, so here this random variable X is this also, notice this notation tilde. Okay, so this tilde notation basically says random variable X is distributed as, or you can read it like that. It's basically distributed as Bernoulli P. Okay, so this random variable has that distribution. Okay, what is that distribution? The range is 0, 1, and then this P parameter, this is a single parameter P, which is a value between 0 and 1, a real number between 0 and 1. It basically gives you fx of 1. Okay, the range is 0, 1, then fx of 1 is P. So now these two have to add up to 1, so fx of 0 is 1 minus P. Okay, so this fully specifies the Bernoulli P, Bernoulli random variable with parameter P. Okay, so notice these parameters. So when we start describing random variables, specific types of random variables, common distributions that you see, these parameters will keep appearing again and again. In the uniform case, the parameter was a set, right? The set over which it is uniform. In the Bernoulli random variable case, the parameter is a number between 0 and 1, which is basically the probability that the random variable equals 1. Okay, the range is 0, 1. The probability that it equals 1 is this parameter P. Okay. So a very typical example is this Bernoulli trials. We've seen these Bernoulli trials before, where you do the experiment repeatedly, or you basically do the experiment, and then there is an event, and P is the probability of success or probability that that event happens. Okay, in that case, you have a very nice Bernoulli distribution. Okay, so again, two random variables, two distributions we've seen already. One is the uniform distribution, the other is this Bernoulli random variable, Bernoulli distribution for the binary random variable. It just takes two values, 0 and 1. Okay, that's why it's called binary in some sense. Okay, the next one is a binomial random variable. We have seen this before. Now the parameters become slightly larger. Okay, so here is the notation again, x tilde binomial n comma p. There are two parameters, n and p. N is a positive integer and p is a number between 0 and 1. Okay. So, for this random variable, a random variable which has a binomial distribution with parameter n and p, the range is from 0 to n, the integers 0 to n, 0, 1, 2, 3, so on till n. Okay. And the PMF is fx of k, k of course goes from 0 to n, right? Fx of k is n choose k, p power k, 1 minus p power n minus k. So, this is the probability that this random variable x takes value k. Is that okay? So, this is the PMF, this is the range, and this is the binomial random variable. See how easy it is to describe random variables, right? So, you have to just say come up with some notation for it, fix the parameters, and then define the range and the PMF using the parameters. That's it. So, that gives you random variable after random variable, isn't it? So, here's an example. You can see that number of successes in n independent Bernoulli trials will be a binomial random variable, right? So, we have seen this before in the earlier lectures. So, this clearly is a binomial random variable. So, as an aside, you have to check that this is a valid PMF, that you can do each of these probabilities each of these numbers is bigger than or equal to 0. How do you check they add up to 1? I described this when describing the binomial distribution. There is a formula here which shows that this is equal to 1. Okay. Anyway, so I'll leave it aside. I'm not going to prove it for you, but you can show that this is a valid PMF. Okay, so this is binomial random variable. You have seen 3 already. Slowly they are becoming more complex. Uniform was just the same value assigned to every outcome. Very easy probability distribution. Bernoulli already was a bit biased, 0 and 1. You put a biased probability. You assigned an arbitrary parameter p to the probability of 1. It could be 0.9, 0.1. That happens quite often, right? Some things happen with very low probability. You can't say everything is uniform, right? Some events happen with very low probability, and you want to be able to do a bias thing. So, here is binomial. Again, this when some repeated trials happen, number of successes end up being binomial. So, this is a distribution that's very common as well. Okay. The next distribution is called, next random variable of interest is called geometric random variable. This has only one parameter p, okay, geometric p, and p is between 0 and 1, and the range is a little bit more complicated. Range goes from 1, 2, 3, so on and on and on and on forever. Okay. And the PMF fx of k is 1 minus p power k minus 1 times p. Okay. So, this is the PMF. You can check that it's valid. You can just sum up over all possible k. You will see it's p plus 1 minus p into p plus 1 minus p squared into p, etc. You use the geometric formation, you will get 1 minus p by 1 minus p, and that's equal to 1. Okay, so that's for p strictly between 0 and 1. If p is 0 or p is 1, you can quite evidently see that things will work out. Of course, p can't be 0, I think. So, I think maybe that possibility is wrongly mentioned here. So, I guess p has to be okay. So, this is the geometric random variable. So, once again, so if you say x is distributed as a geometric random variable with parameter p, p will be between 0 and 1, and range is 1, 2, 3, so on, and the value of the PMF, right, PMF is defined as 1 minus p per k minus 1 times p. Okay. So, once again you see the same principle is being used. You define the range, define the PMF, you fully define the random variable. And from what we have seen before, if you do repeated independent Bernoulli p trials and you want to look at the random variable which is, or look at the number of trials needed for the first success, you get a geometric random variable, isn't it? So, this is clearly the probability for that. Okay. And you can check it's a valid PMF. And I want to point out one thing. Quite often people will describe the geometric PMF by starting at 0 instead of 1. Okay. So, I have started at 1. Quite often people will start at 0. Okay. It's just a convention. Some people start at 0, and then in that case the PMF will be slightly different. That's all. Okay. It's just a convention, but in our course we will start at 1. Okay. So, that's the geometric random variable for you. Okay. So, we have seen 4 so far: uniform, Bernoulli, binomial, geometric. Okay. So, all these 4 we have seen before in different forms. Maybe we did not use the notion of a random variable definition, but we have seen these distributions before. They occurred in sample spaces also, and we described them in terms of just pure theoretical sample space, events, outcomes, etc. We described this distribution. Okay. So now we are studying it once again. We're just calling them as random variables and using them. Okay. So the next couple of distributions we're going to see are new. You may not have, we've not seen them so far. The first one is what's called a negative binomial random variable. Once again, there are two parameters. If you say x is a negative binomial r comma p, where r is a positive integer and p is between 0 and 1, the range goes from r, r plus 1, r plus 2, etc. And the PMF is given by that formula, k minus 1, choose r minus 1, 1 minus p power k minus r times p power r. Okay, so this may not be immediately apparent to you. The trick is to look at the case when r is 1. Okay, so it turns out when r is 1, this becomes a geometric random variable. You can go back and see that if r is 1, range is 1, 2, 3, etc. And if r is 1, the k, the combination goes to 1 because you have k minus 1 c 0, 1 minus p power k minus 1 times p, right. So that's exactly the geometric distribution for r equal to 1. Okay, so it turns out the negative binomial is a generalization of the geometric distribution. Remember, geometric distribution arose as in repeated independent Bernoulli trials, the number of trials for first success. Okay, so the negative binomial is number of trials for r successes in repeated independent Bernoulli p trials. So how long will it take for you to get r successes? And this is the formula for that. Okay, so you can check that this is a valid PMF. It's a little bit more complicated, but not that hard. You can try it. It'll give you some comfort in summing up series. Okay, so that's the negative binomial random variable. I've shown you how it arises. So sometimes you may want two successes when you do Bernoulli trials, right? So what is the number of trials needed for 2 successes? That will be a negative binomial random variable with parameter 2 comma p. Okay, so that's the negative binomial random variable. It's a new one. We're seeing it for the first time in this lecture. The next random variable, which has huge number of applications in practice, is what's called the Poisson random variable. Okay, so the name Poisson is after a French mathematician. The word Poisson in French means fish actually, but anyway, that's also a name of a person, and this random variable is named after that person. Okay, so what is a Poisson random variable? It has one parameter lambda which is greater than 0. Okay, so it's a non-negative real parameter. Okay, so it's not a integer parameter. It is a non-negative real parameter. It is taken greater than 0. So this is a very popular and important random variable for us to understand. It has one parameter lambda. I've been talking about it. Lambda is greater than 0. It's a non-negative real number. Okay, so far we've been using integer parameters. So this is a real number, non-negative real. Okay, and the range is 0, 1, 2, 3, etc. Okay, again non-negative integers are the range. Okay, 0, 1, 2, 3, etc. And the PMF is given here. The exponential function is involved in the PMF. It's e power minus lambda times lambda power k by k factorial. If you want me to write it a bit differently, fx of k equals e power minus lambda times lambda power k by k factorial. Okay, so this is a very famous and popular PMF. It's the Poisson random variable. Okay, so this table shows you the PMF for small values of k. K equals 0, it's e power minus lambda. K equals 1, it's e power minus lambda times lambda. K equals 2, it's e power minus lambda times lambda squared by 2 factorial, 3 factorials, 4 by 4 factorial, etc., etc. You can check that this is a valid PMF. It's very easy. You just use the expansion for e power lambda. So if you add it up, you'll get e power minus lambda times e power lambda. That will go to 1. Okay, e power minus lambda plus lambda, e power 0, 1. Okay, so this is a very definitely a valid PMF. So if you want to see how it looks, here are a few sketches. You can sketch this Poisson PMF. I've used a simple application to sketch it. For different values of lambda, I've plotted the PMF from 0 to 20. And you can see as lambda increases, the peak of the PMF seems to keep shifting, right? So when lambda is 0.5, the peak is close to 0. When lambda is 5, you see the peak is sort of close to 5. When lambda is 10, the peak is sort of close to 10. The lambda is 15, peak is close to 15, and it has moved off to the right. Okay, so this is true in general. If you keep increasing lambda, you'll see that the Poisson PMF keeps shifting. So this is a very significant PMF. It's got lots of practical applications. We will see it later on, even in this week's lecture, one application of the Poisson PMF. Okay. The final random variable common distribution that we will see is what's called the hypergeometric random variable. It's got 3 parameters, all of them positive integers, n, r, m. Okay, so if I say a random variable x is hypergeometric with parameters n, r, m, the meaning is a little bit more complicated. Okay, so to understand the meaning, let's look at the primary example where this is used. Okay, so in this hypergeometric distribution, typically this is the scenario where it's used. You consider a population of n persons. There are n people in the population, the group of people, and r of them are type 1, n minus r are type 2, maybe male, female. You can think of it like that if you like. If you have a 2 gender group, then you can have r of them being male, n minus r being female. Okay, and then somebody is selecting m persons from this group uniformly at random without replacement. Okay, so you pick m persons uniformly at random without replacement, and then my random variable x, if I say, is the number of type 1 people selected. That is a hypergeometric NRM random variable. Okay, so it's a distribution. It arises in sampling like this. Okay, so it seems a bit complicated, but you can see why it is very, very useful, right? So you imagine the disease incidence example that we saw, right? A type 1 could be people with the disease. Type 2 is people without the disease, right? When you pick m samples uniformly at random, one after the other without replacement, that's what you do when you're sampling, right? You select people and test them for the disease. And this x is the number of type 1 people selected. So this distribution is very important in practice when you sample. Okay. So to understand the range of x, you notice it's a bit complicated. It's going to depend on n, r, and m in a funny fashion. So here the dependence is finally given here. The answer is finally given here. It's from max of 0, comma m minus n minus r, comma so on till min of r, comma m. Okay. So a few illustrative cases are given here. Suppose n is 100. We fix n as 100. And let's say r is 50. So there are 50 people of type 1, 50 people of type 2. And I'm picking 20 people. Okay. So in that case, my random variable x could have 0 to 20, right? I could have 0 people of type 1 up to 20 people of type 1. Now on the other hand, if my r is only 10, there are only 10 people of type 1 and I'm picking 20, okay, there's no way I can have 20 people of type 1, right? So my range will go from 0 to 10 only, okay. On the other hand, if my r is 90 and I'm picking m of 20, there are only 10 people of type 2, right? So I should definitely have 10 people of type 1, whatever I pick, okay. So my range will start from 10 and go to 20. So you see these 3 cases are 3 different cases that can happen depending on the value of n, r and m. Okay, so those are illustrative, and all this is condensed together in this max of 0, comma m minus n minus r, comma all the way to min of r, comma m. Think about it, prove why this is true. That's the range of x. Like I told you, range can become complicated. It seems like a simple thing, but you know, it involves some logic in putting things together. Okay. So what about the PMF? Okay, so the range was given to you. What is the PMF? Once again, I'll give you the formula. So I'm not going to prove this formula for you. You can see why this is true, right? So you have, you have a population of n, r of type 1, n minus r of type 2, right? I'm picking m. I want k of type 1. So what is the favorable case for me? R choose k, n minus r choose m minus k. That you multiply, divide by the total number of possibilities, n choose m. So that's the PMF for you. Okay, so this is the hypergeometric distribution, hypergeometric random variable, and I've specified the PMF for you. Okay, so I think this is the last slide that I have here. So that summarizes the common distributions that we are likely to see in a course like this. So we had the uniform, we had the Bernoulli, we had the binomial, we had the geometric. We have seen this before. We had the negative binomial, which is a nice generalization of geometric, number of trials for r successes. Then we had the Poisson random variable. We have not yet seen an application. We'll see it soon enough. It occurs quite often, surprisingly often. And then we had the hypergeometric random variable, which arises in sampling. Okay. So with that, we'll conclude this lecture and move on to the next one.